Hey everybody. So today we're continuing our dive into integer programming, and I wanted to look at a famous integer programming problem. This one's studied a lot because it's kind of interesting and famous. It's actually pretty simple. It's called the knapsack problem. And it goes a little bit like this. So let's say that you're an antique collector and you travel the globe trying to find antique pieces to sell in your shop. While you're on a trip to Europe, you come across the most valuable set of artifacts that you've ever seen, and they're completely free. They're just giving them away. So you could take whatever you'd like, and you'd like to take it all. But there's a big problem. You can't just put these things in your luggage. So for safety, they're really, really breakable and really, really valuable. You'll have to place them in your carry-on bag. And the airline you're traveling with, you're only allowed to carry on 35 pounds. Anything greater than that, let's just for simplicity's sake say that they will not allow you on there with your bag. So each item has a weight, but it also has a value. So you'd like to choose the combination of the most valuable antiques while staying under 35 pounds. So that sounds pretty simple, right? That's called the knapsack problem. So this falls under integer programming because you can't take a piece of an item. You're not going to break the antique teapot in half and try to sell it for half price. You have to decide whether to take something or not. I wanted to introduce this one because this will be our first binary or 0-1 integer programming problem that we've solved. So this gives us a way to model things mathematically, either all or nothing. You take this thing or you don't. You choose this thing or you don't. Kind of a yes-no mathematical ability to make decisions. And it's how some people use optimization to make decisions, is by making programs and the choices are 0 or 1. And you do it as an integer programming problem like this, and you can choose yes or no based on your 0 or 1 response for each variable. Okay. So how would we model this? Well, it's actually pretty simple. We want to first note that we're going to have so many items. We'll just say n. Each item has a value and it has a weight. So we would like to keep the cost, we would like to get the cost as high as we can while keeping the weight under whatever the limit would be. So I've spoiled and given away a little bit of our decision variables. Our decision variable would be for each item. Oops, let me get a pen. So you could just label them item 1. Do we take this item or not? And so that would mean that this has got to be either 0 or 1. 0 or 1. Those are the only choices. Okay? So x could be 0 or 1. x2, the same thing. It could be 0 or 1. Okay, all the way out to xn. Most people will just write this as a vector, an in length vector, where each thing is a 0 or a 1. Okay, so it might look something like this if you had 4 items to choose from. That's how I'm going to do it, as kind of lazy suppressed notation. Okay. So what constraints would we have, and what would our objective function be? Well, the objective function is the easy part, right? You're wanting to maximize the value. So whatever the value, say the C is the value, we'd like to maximize that. So every C would get multiplied by its x, its decision variable. So if you choose to take x1, it would have a 1 there, right? So you get that value. If you don't choose to take one of them, that would be a 0. 0 times the value, so you don't get that value. And so we would do this for all n of these items. And so that should kind of give you an idea of how the constraints are going to look. So it has some sort of weight, or in this case, literally a weight. And so each weight will be multiplied by its decision variable. And of course, if you choose to take x1, that will be a 1, so we will count the weight. If you choose not to take something, that'd be a 0, so you don't take it, and it's got to be less than or equal to whatever that limit is. And then, of course, all the x's. Another way of writing this is they've got to be between 0 and 1, and they have to be integer. Or another notation is to say that x has got to belong in the set of 0, 1. Or you could write it this way: x is in the set of 0 to 1, but it's got to be integer. There's lots of different ways to write this. Okay, so that's how we would model it, though. Maximizing all the cost, subject to all the weights being below our limit. Now, so if you're just thinking logically, without any background knowledge in optimization, you would think that we'd have to do this combinatorially. We'd have to literally look at every possible combination of weights if it's complex enough to where you can't just look at it and decide these are the best things to take. And that kind of seems right at first, but there's other ways to do this. So I do want to give you a little background about it. It's one of the most famous integer programming problems. It's been around a long, long time. It was nicknamed back as far as 1987. Now, operations research is not that old, so it wasn't an operations research problem by then. It was just someone kind of puzzling. Mathematician Tobias Danzig. He refers to this problem. It's kind of been mentioned a lot throughout history. But I will say this is a very useful problem because companies use this in resource allocation or deciding what to do, decision making. So like say you have projects. Like out here they've been working on the road and they have all these different crews, and when what crew works, I feel like they don't do a very good job optimizing the time. Sometimes I get really tired of the road construction. But anyways, it can be used in a lot of real world situations. So let's actually do an example of our knapsack problem. Okay. So you're moving. You've rented a truck and you can haul up to 1,100 cubic feet of furniture. The volume and value of each item that you are considering taking with you is in the table below. What should you take with you to bring the most value? Okay. So you're taking your bedroom set, your dining room set, your computer desk, your sofa, and your TV set. There's the value and there's the volume, right? So how can we do this? We could, first let's model it. That's how it would look as an integer programming problem or written out. Notice I just maximized all the values. All the weights or all the volumes, all the measurements of it have to be less than 1,100 because that's all the truck can hold. And I put that x1 has got to be 0 or 1. So how are we going to do this? Well, last class we learned how to do branch and bound, and we worked an example. Was that last class or 2 classes ago? I think we learned it 2 classes ago, and I worked another example last class. We can use, even though these are not all the integers, 0 to infinity, this is integers 0 to 1. So this actually kind of simplifies the branching here. Now, I worked this problem out. It's kind of long, so I'm going to skip showing you the solve. Just trust me, I used my solver to solve each of these. I did not do all these by hand. So let's start with node 0, and I hope that I can fit all this on there. So if we just solve this as is, dropping the integer constraints, what you get is an objective function value of 86.5. Trust me, I did this. And x will be equal to 0.125, so not an integer. 1, 0, 1, 0. And you say, okay, well, to branch and bound, we're going to want to branch on x1. So there are 2 choices for branching on x1. Either x1 is equal to 0, or x1 has got to be equal to 1. Okay? That'll give us the nodes 1 and 2. So those are your 2 choices. Instead of less than or equal to some number and greater than or equal to some number, it's equal to 0 or equal to 1. So you're stuck with sticking it to one value or the other. Now this tree gets really big and really nasty, so I hope that I don't, I hope I can fit it all. I had a hard time fitting it on my piece of paper, much less on the smartboard here. So let's see. So when I solve this one, when I say, okay, well, x1 has got to be 0 going down this branch. If x1 is 0, you solve it, you get z equals 84. And x equals, still not integer, 0, 1, 0, 1, 1 half. Okay? That's not a huge deal. But we'll need to branch on x5, so x5 equals 0, or x5 equal 1. Before I go down that way, let's branch here. Oh, well, let's solve here first. Sticking x1 equal to 1, I solved it, and I got z equals 84. Same value, same objective function value as the other is node 1. And you get 1, a half, and then the rest are zeros. So still not integer, so we'll need to branch on x2 with this one. x2 equals 0, x2 equals 1. Okay, so let's solve all these problems. Node 3, 4, 5, and 6. So if I solve node 3, where I say x5 has got to be 0, x1 has got to be 0. Let's see what I end up with. Using my solver, I got z is 83 2/3. So you know, not an integer again. This does grow to a large tree. 0, 1, a third, 1, 0. So this one will be branched as well. Let's look over here where we say x1 has got to be 0, x5 has got to be 1. Z equals 81.25. So once again, not an integer. We haven't hit an integer yet. This one takes a while. 0.75 and 1. So we'll branch on this one. This is where we'll start to get out of space a little bit because it's kind of crammed. Okay, let's see. If we stick this at 0, I'll start writing in. Maybe I should have written in different colors. I'll do this half in a different color. Z equals 83.25. Not an integer again. 1, 0, 0. 0.75, 0. And then over here, finally a branch ends. This one is infeasible. So we can cut this one off, thank goodness. So that one's done. But the rest of them need branching on, so this is a rather large tree. If we're trying to squeeze stuff in, I may go ahead and branch on, well, let's see. Let's branch on node 3. Trying to go over there as far as I can. Let's see, what am I at? Node 7, node 8. We're getting really large here, right? So x3 is the problem child this time. x3 is either 0 or x3 is 1. I do want to point out, what happens if I had 2 integers here? Well, you just fix one and keep going, and you just choose one to fix. And then you keep going, and you may have to deal with the other one later, or it may sort itself out. So finally, over here where I say x3 is 0, x5 is 0, x1 is 0, we get an integer solution. So this one can stop. Z is 79, and x equals 0, 1, 0, 1, 0. So you're taking the second and the fourth item. Now, this is very important to note, because we have an integer problem. Even if it's not an integer, if any of these end up below 79, I can cut them off and stop, okay? So far, this one's not below 79, this one's not below 79. But if they do go below 79, I can say, finally, I'm done with that piece of the branch. Because remember, so that would save us some calculation, right? As you work down a branch, the z value only gets lower. So if I end up cutting here and I get 77, then there's no need to branch anymore, because even if they come out integer, they will be less than 79. Okay? So now if I were to take x3 equals 1, you would get z equals 77.5. I don't even care what x is, but I'll give it to you. 0, 1, 1, a half, 0. So you'd want to branch, but we don't have to because 77.5 is less than... So if you didn't know what you were doing, you would have a huge tree here. But I'm going to say, let's cut this off because 77.5 is less than 79. We're maximizing. So going further would just be lower than this, which stands no chance of beating 79. Okay, whew. So still branching, still working, because these two could beat 79. I got to branch on x4. So x4 could equal 1, up 0, and x4 could equal 1. Okay, when you do this, this one gives you an integer, so thank goodness this one can stop. But z is going to be 72. It's not going to beat 79, but it is another integer answer, so that's fun that we at least got another one. But that's not the optimal. But I can stop there, thank goodness. If x4 is fixed at 1, z will be, let's change color so it doesn't tangle together. Z is 81, and x is 0.833. So this one can branch again. Do we want to branch? Yeah, because it's 81. It's above 79. Okay, so this one will need to branch again. Node, oops, I forgot to write my nodes, 9 and 10. Node 10. Now, before we branch here, let's go ahead and look at this one. This one needs to branch. Because this is getting so long, I'll go ahead and go a little faster and spoil some of it for you. This one ends up being some z value of 74 and 2/3, but there's no need to continue because that's less than 79. And this one ends up being infeasible. So this side is done. So none of these choices are working out. So we just got to branch here to see if it can beat 79. Okay. In this point, we're almost all the way to the bottom of making all the decisions, right? x1 is fixed, x5 is fixed, x4 is fixed. Here, x2 will be fixed. x2 equals 0, x2 equals 1. I told you this is a sloppy tree. If we fix x2 to 0, we do get an integer answer, but it is all the way down to z is 55. Very, very much lower than 79. So we can stop there, and this one is infeasible. So finally, we finished this giant tree. There are only 3 integers to choose from. Which one has the highest objective function value? 72, 75, or 79? 79. Thank goodness. So we have an optimal. It's a value of 79. And it says that we are going to take the second item and the fourth item. So we're leaving the first, second, third. So that's the most value that we could take with us to fit in this moving truck. Okay, so what was the second and third item? The dining room set and the sofa. So at least you can eat and you can sit on the TV, but sit on the sofa. Guess you're not taking the TV or your computer desk or a bed. So maybe not the best decision when it comes to logical thinking, but there's your optimal. Okay. Now, so we can use branch and bound for 0, 1 integers or variables. Was there a better way to do this though? Can you just think about another way of doing these instead of having to do branch and bound, or instead of having to think of all the possible 1 and 0 combinations? This is just trying to choose the most valuable thing. So some people say, hey, let's just go with a greedy algorithm. Let's just choose the most expensive, 60. And then the second most expensive, that won't fit because 800 plus 600 is more than 1100. But that would make you miss the answer, right? The optimal, because if you chose a 1 there. But there's another way of thinking about this, okay? There's another way. There's some simplicity built into these simple knapsack problems. What if we thought about the unit value, okay? And when I say the unit value, what I mean is if we were to take what's in the objective function by the value, which we call the cost, and we were to divide that by the weight, okay? This can be interpreted as um, the value per unit of the resource. Because this, I say resource because this could be weight, it could be volume, it could be time, it could be whatever we're weighting each thing with. Okay? So that way, we could actually solve it kind of like a greedy algorithm. If you don't know what a greedy algorithm is, that's where you pick the one with the most value. So if we're going to be picking the one with the highest ratio. So it's almost like a greedy algorithm. Almost greedy algorithm, which is actually pretty simple. Now here's where we have to get a little careful. Okay, so say I pick an item that has the most value, and I pick the second item that has the most value. There's still space left in my knapsack, but the third item won't fit. So we do have to cycle through each item and say, okay, well, will the fourth item fit? Because you might have 1 pound left in your backpack, and you can't take any of the really expensive things, but you've taken the most expensive. But you could fit one more little thing in to add another dollar to your value. So you do have to check through all of them to see if anything fits. So I've set this one up for the greedy algorithm. Noticed instead of the value, I have the cost divided by the volume. Okay, or the value divided by the volume, which gives us these decimals. So what we could do is we could say, okay, let's see. What's the, remember we call these x1, x2, x3, x4, and x5. Without remembering the answer, what's the most bang for our buck? The dining room set, x2. We still have to pay attention to the weight because that's 600, right? What else? What's next? Oh, this one, 775 is more than 75. So this sofa is x4, and it has a value of, or weight of 400. Remember, we had to keep it less than or equal to 1100. So that's a 1000 already. Is there anything that has a value, a weight, a volume of 100? No. So I can't fit anything else. So this, using this style, it says that I would take x2 and x4. What was the optimal solution? Yeah, remember it was taking x1 and x4. Not that you should accept this as proof that it always works. You should go and look at it yourself and see what you think. But we did come up with the same solution. Okay, just using the simpler greedy algorithm. But knapsack problems are awesome because they do give us a chance to experiment with a lot of different techniques for solving integer problems, because they're not that hard to solve, but it's fun. You could do branch and bound. You could do this method right here. You could do some other heuristic solving, some other ways of solving. You could do combinatorially, where you look at every single combination, not the most sufficient way or efficient way of solving, but a way to solve. But anyway, so that's the knapsack problem, and I want you to start to notice that, okay, we could program things with our programming, model things with zeros and ones, and be able to then just make decisions mathematically where either a zero is a no and a one's a yes. Do I need this? Yes or no? No, it doesn't fit into my day. No, it doesn't, and get the biggest value out of things. So some people call this operations research. They call it decision-making mathematics because of those type of things. Anyways, I'll let you go. Y'all have an awesome day.